Next up is Jacob Thoma of NASA Jet Propulsion Laboratory. He'll be talking to us about PITH, using an open source C interpreter for integrated testing and in-flight debugging. Jacob.
Hi, everyone. My name is Jacob Thoma, and I work on Spacecraft Flight Software at JPL. Like was mentioned, I'll be talking about PITH, which is our backdoor testing and symbol access module that uses an open source C interpreter called PICO-C. PITH is an acronym that stands for the Platform Integrated Test Harness, and we use it for integrated testing, which I'll get into more later, but it's basically flight-like runtime testing. And we'll also eventually use it for in-flight fault investigation and recovery as necessary. It has two main parts: the PITH application, which includes the open source C interpreter called PICO-C, and a library of compiled Psyche-specific utility functions. So these are things that would let us peek and poke memory or call a flight software function. The other main part is a group of what we call servlet threads, with one running inside each partition. And that's necessary due to our flight software's time and space partitioned architecture. So the servlet threads are kind of acting on behalf of the main PITH application to do work. Next slide. So a little bit of background on Psyche Flight Software itself before we get into PITH. It's a branch off the JPL Flight Software core product line, or FCPL if you've heard of it. And the important thing is it utilizes time and space partitioning, which a lot of you are probably familiar with, but the basic idea is that modules are divided into functional areas called partitions or components. The space partitioning aspect of it is just that partitions have their own virtual address space and can't access each other's memory without an explicit shared memory region. The time partitioning side of it is that partitions are allotted a static amount of runtime in a recurring schedule called the minor frame. So I drew up kind of a little example down there. You can see these 4 example partitions are running in this recurring schedule, and they each have a static window to run in. And then within each individual partition window, there's basically a main thread that does all the processing, and that has to finish before the end of the partition window, or flight software will reset. But then there's also something called a non-deadline enforced thread that gets to use any of the leftover time in a partition window. And so PITH actually runs exclusively on these non-deadline enforced threads that use up the extra time in the static schedule. Next slide. So for a little bit more of a structural view of how everything is connected, I have a few example partitions, so like uplink, downlink, guidance and navigation, and they each have their main 16 hertz process and then this non-deadline enforced servlet that will run afterwards. And they are talking to the PITH application, which is in a separate partition using inter-process communication, which is a service provided by a different flight software module. And so you can also notice that there's a servlet in the utility partition, and that is just for symmetry of the messaging, so it looks nicer when accessing symbols within the utility partition, even though the PITH application technically could access those. Next slide. So for our use case where we're running off nominal code at runtime, either for testing or fault recovery, we could compile a little piece of code and schedule it to run, but we went with an interpreter. And really the main reason is it provides a nice layer of abstraction, so that little script doesn't have to deal with dynamically linking any libraries or IPC messaging itself. It can just kind of call these library functions and everything is handled on the back end. And then another nice thing is if there's a bug in your PITH script, it can just give you a line number that the script failed and abort parsing the script instead of possibly failing an assert or causing an exception that would force a full reboot of flight software, which at the very least when you're testing is a lot of time. Next slide. So then why did we pick C for our interpreted language? A big reason that it was easy for developers to use because they can use source code enumerations and type defs in their scripts just like they were writing compiled C basically. And that's enabled by an autocoder in the build process that actually goes through all the header files and pulls out the type defs and enums and preprocessor directives and creates a bunch of char arrays in a build product that PITH can look at and interpret directly when you hash include a header file. C also certainly has ample language support for complex tests. We don't really need any more functionality than C offers. Even though PicoC doesn't quite implement all of C99, it does a pretty good job. It's mostly complete and certainly enough for our use case. The C interpreter also has a lightweight code base at only around 7,000 lines. So that means it's easier to debug the interpreter itself or to add features and things like that. And lastly, it enables runtime unit testing. So our old unit testing system, they were C tests written in C compiled for Linux. And the integrated tests feel a lot like the unit tests since they're also written in C, but have access to a lot more functionality. Next slide. So the integrated tests, the main idea is that they leverage the fact that the whole system is running. So the services and APIs from other modules are all available, and it's a very flight-like test environment. So it's kind of forcing the running system into some state that it could theoretically find itself in while in flight. And with this integrated testing, we've achieved pretty good code coverage, over 95% on complex modules, with most of the remaining uncovered code being like default assert statements in a switch case. And then PITH also, in addition to providing those peek and poke memory utility functions, provides some testing infrastructure functions. And so you can build tests around this notion of expecting a value. So maybe you expect some function called to return success, or you expect the contents of some bus transaction to be something, and then at the end you will report the results of your test, and it has a pretty nice standardized interface. Next slide. So to give you a kind of simplified, generalized idea of what a PITH script looks like, it basically just looks like any C file, and you can hash include a source code header at the top, and then there's a main function with argc and argv like you're used to, and you can actually pass in the ground command arguments to argc and argv like you would at command line. And then there's some testing infrastructure functions, so you would declare that the test is starting and then have some values you're expecting. Here we have 1 equals 1, 2 equals 2, 1 equals 2, and so obviously we expect 1 out of 3 of these to not pass when we report the results, and then that's what we see. Next slide. A little bit more about PicoC. As I mentioned, it implements a large subset of C99, with the biggest missing thing being function pointers, but for our use case, if you find yourself needing a function pointer, your test is maybe getting unnecessarily complicated. So that was fine for us. We did have to add some features that PICO-C did not have implemented, but we otherwise needed. Stuff like some of the preprocessor directives that we had used in our header files, like undef, elif, were not defined, and then some stuff with getting the sizing on the 64 32-bit ints to be correct, and then also floats versus doubles sizing to be correct. PICO-C is given a statically allocated memory buffer at initialization time to use as its heap and its stack, and so it grows the stack from one end of this buffer and the heap from the other. And this buffer and other PICO-C state is cleared after each script is run. And this means another advantage of the interpreter is, instead of getting a stack overflow, if like the heap meets the stack in this buffer, PICO-C can just say, oh, we're out of memory, and abort parsing the script instead of causing an actual stack overflow and crashing flight software. And then PICO-C has this concept of a platform file that defines the mapping of the interpreter internal function signatures, which are just a bunch of strings of the function signatures, to a set of the compiled Psyche library functions. And within those compiled library functions, you're probably going to be sending an IPC message to the appropriate servlet to perform work. Next slide. So from a high level, to connect the dots a bit, running a PITH script from start to end. So you uplink the C file to the file system, and it contains a main function. Then you send this execute PITH script ground command with arguments that include the file name and possibly the argc, argv arguments. Then the PITH application gets the command and makes a request to the file system, where it parses the script, and then if nothing was wrong, then it calls main. And inside calling main, if it encounters a Psyche library function, then it calls the corresponding compiled function, which will likely send a message to a servlet running in the appropriate partition that you want to do the peek or poke in, and then the servlet is just sitting there waiting, and it gets the message, and then it does whatever it's asked to do and returns the results, and then the compiled library function takes that and returns that to PICO-C. So it's made available inside the interpreter. Then eventually the script finishes running and PICO-C is reset. So it memsets this heap to 0 and calls other cleanup functions. Next slide. Some of the library functions that are available, I've mentioned a lot of them. Some are the symbol address lookup, peeking and poking memory, calling a function with any signature in any partition, and that includes public APIs and libraries that a partition is linked in at runtime, which is pretty handy. You can inject ground commands, you can read, write, and delete files, log bus transactions, and then look at the actual content of the transactions and make sure it's what you expected. You can log and verify what we call system-wide event reports, and then lastly, send messages to our simulation and support equipment. So you could do something like turning off an individual device sim, like let's say the Star Tracker sim, and then make sure that the Star Tracker Manager module responds properly to that device becoming unresponsive. Next slide. I think I've covered the servlets a lot, but basically they are just sitting there running as non-deadline enforced threads in each partition, and they're just waiting for an IPC message from the main PITH application, which will describe what work needs to be done, and then they will perform the work and send a reply with the result back over IPC. Next slide. A little bit more about some of the specific library functions. So the symbol address lookup is also enabled by another autocoder in the build process. And this one creates a big array of symbol names, addresses, and size for every symbol. And so the individual servlet can look in this big table and check for the address of a symbol before it calls this slower OS provided symbol lookup function. Next slide. And then peeking and poking memory is another big one. And so this gives us the backdoor symbol access in any partition. So an example you could use this for in an integrated test at least is checking that a specific field in a module's global state struct is updating properly, maybe after you injected a ground command or something like that. And what's handy about PICO-C is since it's C, you can just read that data into a struct pointer in your script and then examine it with normal struct syntax, which is pretty nice. And then another thing you could do is update the health state of a device to sick or dead and observe the system response. Next slide. For calling functions, we looked at how our compiler passes function arguments. Basically, most of them are passed in registers 3 to 10, and then structs are passed on the stack and the address gets put in a register. And so all we really needed to do was construct the correct argument list. So that IPC message includes all the arguments, and then you look up the address of the function and cast it to a function pointer and call it with all your arguments in the correct location. Next slide. PITH also provides a public API to the bus manager modules for logging bus transactions to a shared memory region so that your PITH script can examine the contents of these bus transactions and make sure that proper transaction was sent out and maybe that the status was okay and was expected. Next slide. Then a little bit more about the source code headers. So this was something we ran into kind of early, was developers were having to copy paste big chunks of type defs and enums from their header files into these scripts to really do anything useful with them. So we ended up compiling the scripts or the header files as char arrays into the flight software for PITH to use. So you can see this one on the top is kind of just a dummy header file. And then after it goes through the autocoder, all the comments get taken out, all the unnecessary spacing gets taken out, and you're just left with the preprocessor directives and the type defs and the enums that then when you hash include this header file, then the interpreter can just go ahead and parse this script or parse this char array just like any other script. Next slide. And then lastly, PITH provides a shell kind of interface, which just lets you access the servlets in a different way than through a PITH script. So you can do things from a sort of command line interface like peeking and poking memory and examining the files and calling functions and things like that. Next slide. So in conclusion, PITH is a tool for flight software developers and the internal test team to test their modules in a flight-like runtime environment. It has achieved greater than 95% code coverage on complex modules. And also it's a tool for in-flight fault investigation and recovery, given that has backdoor symbol access and can call functions from within any partition. Next slide. And I'd just like to thank the PICO-C developers. Obviously, Zik Saliba was the main contributor, and Dan Gaines from FCPL, who developed the precursor to PITH, and then the whole Psyche Flight Software team, especially Dave, Chris, Ryan, and George. So yep, that's it. Any questions?
Thanks a lot, Jacob. We do have a few questions. Some of them landed in the Q&A, others in the chat, and others were sent to me. So let's see. First one is from Amale Oyaki. No, I mixed that up. That first was from Matt Benson. Sorry. Is the Flight Software Core product line available outside of JPL? And if so, who would one talk to about this?
To my knowledge, it is not available outside of JPL, but is possibly being used in future missions. Yeah.
Okay. All right. Next one from Ryan Niemerhoff. How much overhead is there in interpreting header files at runtime?
So yeah, that can take certainly a tangible number of seconds to interpret a lot of header files, particularly if there is a big web of inclusions, because one header file if it includes like 20 other header files, then PICO-C has no choice but to follow those all the way down to the end of the tree. and so that can take some time, but fortunately speed is not really a priority here.
Okay. All right, next question from Peter Fiddleman. How does the memory peek poke feature interact with Psyche's space partitioning? Is each servlet limited to peeking, poking in the memory space of its corresponding application?
Yep, so there's a servlet in each memory space, basically, and you would give an argument of which partition you want to peek and poke in your PITH script, and then that servlet would do the work in its own virtual address space. And so the individual servlets are limited to accessing their own address space, but we have full coverage since we have servlets in every partition.
Okay. Next question from Leonidas. Before deciding to use PICO-C, did you consider dynamic compilation such as TCC, which can also use a C scripting language?
The actual decision process was happened before I arrived, so I'm not sure if they considered that, but
okay,
it might be good to look into.
Okay, and this may be related. Question from Amalé. What was the trade in considering C interpreter like PICO-C? Did you consider other languages? I think that's related, right?
Yeah, we looked at, well, so this part I know a little bit more about. I think C was chosen just in a large part because it was so small, and then it also had the advantage of developers being familiar with it, and we can use the exact syntax from our structs and enums and stuff. So it had a lot of advantages.
Okay, great. And so some folks were in the chat answering some of these questions, but I think, or commenting on some of these, but I think it's going to the panelists. So we'll copy some of those answers over into the talks Slack channel. Any other questions for Jacob? All right, looks like it's 4:30. Thanks a lot, Jacob. Excellent talk.
Thanks.